Okay, everybody, so this is the question from yesterday that I posted on enthalpy of formation, all right? And I'm going to be giving you guys some a classwork soon on this. So let's check it out. So it was calculate the delta HF, the enthalpy of formation of 2,2,4 trimethylpentane. And I kind of gave you a little bit of an organic review there to see if you could figure out what it was, right? Okay, well, 2,2,4 trimethylpentane is the chemical name for gasoline. That's why they call it octane. They call it octane because it has 8 carbons. So here's the simple line structure drawn out, right? And we got 1, 2, 3, 4, 5 carbon chain, which is a pent. And then you got 3 methyl groups stemming off, right? So you got CH3, CH3, CH3. So since this is a saturated alkane, the chemical formula is CnH2n plus 2. Okay, which comes out to be C8H18, or you could just count them up. All right, anyway. So, unlike the problems before, I gave you the delta H value of the reaction. We're trying to calculate the delta H value of the gasoline, okay? All right, so let's see what we get here when we're throwing this together. Okay, first of all, the delta H value of any element, pure element, is always 0. So O2 would be 0. Something like aluminum would be 0. Nitrogen, N2, would be 0, as long as it's in its elemental form. Phosphorus, which is P4, if you remember, it's one of the friends of all the diatomics. Anyway, okay, but the other ones you can look up on your chart, right? So here's what we got. We got the octane here. Since it's a combustion reaction, you have O2 produces CO2 and H2O. That's every combustion reaction, right? Okay, if there was like a nitrogen compound, you'd probably get some nitrogen monoxide or dinitrogen monoxide, nitrous oxide, whatever. Okay? All right, so let's see. So you got the summation of the delta H values of the products, which are these two, minus the summation of the delta H values of the reactants, and that's going to equal the delta H value of the reaction. Okay? So first things first, you obviously need to balance this equation. And if you haven't done so, right, it's one of those ones that needs to be doubled. So I'm just going to balance it real quick for you with 2, a 25, a 16, and an 18. All right? All right, so here we go. Here's our parts now. Okay. If you went 8 and 9, you would have found out you end up with the odd number of O's, and you'd have to put a, what's half, a 12 and a half there, and then just double it. Okay? All right, so now let's get the delta H values of the products and the delta H values of the reactants. All right, so you have to, I tripped you up a little bit, though, and I put H2O liquid this time. In the problems before, we were using H2O gas, which is negative 241.8, I think, or somewhere around there. But the liquid phase is different. The liquid phase is 285.8, negative, of course. Okay, so let's get the summation of all the delta H values of the reactants. So you look on your enthalpy of formation table, and you'll find that CO2 gas is negative 393.5. The unit is kilojoules per mole. So we have 16 moles of it. So let's do the summation of the products first. So we got, let's see, we got 16 moles, right? And carbon dioxide is negative 393.5 kilojoules per mole, right? Okay, so here's the first part, right? Okay, our mole unit, of course, is going to cancel out like so. All right, so it's the summation of the products. Sorry, I was looking at the reaction. Summation of the products. So this is the first part. CO2 is that, and there's 16 moles. Now we got to do plus. All right, now we have 18 moles of H2O liquid. Okay, so we have 18 moles of water. And in the liquid phase, the enthalpy is negative 285.8. Of course, same unit, kilojoules per mole. And since we only have 2 products, that's going to end up being the summation of the products. Let's get rid of our mole values there, okay? All right, so we're gonna do the summation of the products. Now we got to subtract, right? We're gonna subtract the delta H values of the reactants. All right, but remember, O2, because it's an element in the gas phase, right, is 0. So this part, the 25 moles, it doesn't even matter. 25 times 0 is still 0. Okay, so here we got, let's see, the reactants. Well, the only reactant that we have is the octane, the 2,2,4 trimethylpentane. All right, and I know I have 2 moles of it, right? So I'm gonna say, all right, so it's gonna be 2 moles, right? 2 moles. Okay, but we're trying to calculate the delta HF value of it. So that means we don't know it. And again, anything we don't know, we call X, okay? Or you could call it delta HF. I don't care, really. All right, there we go. Now remember, there's no need to do a summation here because this is 0. All right, now, and that's going to equal, okay, that equals the delta H of the reaction. Well, I have the delta H of the reaction. It's negative 11,018 kilojoules. Okay? All right. So now all I got to do is do some combination here, right? So we got 16 times negative 393.5. Now I already worked this out. So that comes out to be negative 6296 kilojoules. Okay? Plus, all right, now we got 18 times negative 285.8. And that is negative 5144.4 kilojoules. So that becomes my summation of the products. All right? This is way more fun in person when I can be insulting all of you and trying to make you laugh. All right, anyway, so there's the summation of the products minus the summation of the reactants. Okay, well, all I have here, 2 moles times X, that just becomes 2 moles times X. I can't really combine it any more than that, right? And that equals our negative 11,018 kilojoules. Okay, so let's do some more combination here. All right, we can combine negative 6296 plus negative 5144, and that gives me negative 11,440.4, and it's just kilojoules, minus 2 moles times X equals negative 11,018 kilojoules. Okay, then from here, the math should be relatively simple, right? All right, so we're gonna add 11,440.4 to both sides. Since I'm running out of room, I'm just gonna give you what that answer becomes, and then that way we can figure, I'll do the very last step, okay? So what's gonna be left on this side of the arrow, if we add 11,440.4 kilojoules to both sides, I'm gonna be left with negative 2 moles times X equals 422.4 kilojoules, right here in the bright green color. All right, and the last thing, of course, is we're going to divide by negative 2 moles. All right, negative 2 moles. It's a lot harder to write on there than it looks. Negative 2 moles. Okay, and we will come up with an X value of, let's first get rid of the negative 2 moles. We get an X value of negative 211.2 kilojoules per mole, and that would be the enthalpy value of the 2,2,4 trimethylpentane. Okay? that's pretty much it, kids. I'm going to be sending you a classwork, and I'll give you enough time to do it. Don't worry. I know that we're all in a kind of a crappy way right now. I remember doing stuff. That was awesome. Yeah. Back in the day when you could, like, go somewhere. That was fun. All right, anyway, I hope you're all well. Take care, and I'll try to schedule a live session this week for extra help if you need it. Okay? Miss you guys. Hang in there. Later.